Most people hear neural network and imagine scientists building a digital brain inside a computer. Sounds dramatic, but neural networks are not tiny human brains. They are mathematical systems designed to recognize patterns by passing information through connected layers. But here's the real question. If artificial neurons are not real brain cells, how can they still learn to recognize faces, voices, language, and complex patterns? Think about how you recognize a face. You do not calculate every pixel. Your brain notices features: eyes, nose, shape, expression, and how everything fits together. A neural network works in a similar basic way. It receives information, detects small patterns, combines them into larger patterns, and produces an output. A neural network usually has three main parts. The input layer receives the data. The hidden layers process that data. And the output layer gives the prediction. Imagine showing it a picture of a cat. The first layers may notice edges and lines. Deeper layers may identify fur, ears, eyes, and body shape. Finally, the output layer predicts this is probably a cat. Each artificial neuron receives information, gives different importance to different signals, and passes a result forward. That importance is controlled by values called weights. At the beginning, those weights are mostly useless, so the network makes poor predictions. It may see a cat and confidently announce, "Excellent toaster." But during training, it compares its prediction with the correct answer and adjusts those weights. This happens repeatedly through a process of prediction, error measurement, and adjustment. The information moves forward through the network to create an answer. Then the error moves backward so the network can improve its internal weights. This learning process is called backpropagation. The name sounds painful, but the basic idea is simple. Find what contributed to the mistake and adjust it. Imagine a football team that keeps conceding goals. Instead of firing everyone immediately, the coach studies what went wrong. Was the defender too slow? Was the midfield out of position? Did the goalkeeper react late? The coach adjusts each player's responsibility. A neural network does something similar mathematically. It changes the influence of different connections until the overall result improves. A practical example is handwriting recognition. Different people write the same number in completely different ways. A fixed rule-based system would struggle to describe every possible version of the number 8. But a neural network can study thousands of handwritten examples and gradually learn the visual patterns that usually represent each number. A small case study is AlexNet. In 2012, this deep neural network achieved a major breakthrough in an international image recognition competition. It performed far better than many previous systems and showed that large neural networks, powerful graphics processors, and huge image datasets could transform computer vision. That success helped trigger the modern deep learning boom. But neural networks also have weaknesses. They often need large amounts of data and computing power. Their internal decisions can be difficult to explain. And if their training data contains bias or errors, the network may learn those problems too. A complex model is not automatically an intelligent or trustworthy model. The foundations of neural networks go back decades. Researchers such as Warren McCulloch and Walter Pitts proposed an early mathematical model of artificial neurons in the 1940s. Later, Frank Rosenblatt developed the perceptron, an early learning system. Modern neural networks are much more powerful, but they grew from those early attempts to represent learning mathematically. So, in one simple line, a neural network is a machine learning system made of connected layers that learn patterns by adjusting the strength of their connections. One neuron does very little, but thousands or millions working together can recognize extremely complex patterns. Welcome back to the AI Studio, where we make artificial intelligence simple, visual, and slightly less painful. But if neural networks have existed for decades, what changed when researchers made them deeper? And why did deep learning suddenly allow machines to see, hear, translate, and generate human-like language?